Hello, Professor Schumacher here. We're going to do a demonstration of the phenomenon of nuclear magnetic resonance. This is an animation based on VPython that you might find interesting to learn how this physics phenomenon works. The program that I'm going to show you is available at the bottom of the screen here as a link, and there's a QR code that will take you there as well. This is a fairly long demo, so here's a kind of an agenda of what we're going to cover. The first thing will be, I'll show you the layout of the demo on the screen, and then we'll talk about the oscillating radio frequency field that you have to match to the Larmor frequency of the sample protons to get the phenomenon of magnetic resonance. Then we'll talk about the internal field gradients that complicate matters a little bit initially, and the phenomenon of free induction decay. Then there are two things that we're trying to measure. First of all, the so-called spin-spin relaxation effect on a time scale known as T2. And there's a famous trick called the spin echo effect that involves a particular sequence of RF pulses to make it visible. And then the other one is there's a second relaxation phenomenon called the spin lattice effect, which is measured by a time called the T1 relaxation time. And there's a different pulse sequence we need to look at and admire to understand how that works. All right, so here on the left side of the screen, I'd like you to imagine this is our sample. The little green arrows are individual spins in the sample. This might be a biological sample, a protein which has a lot of protons hanging around, and each one of these green arrows is one sample element, one hydrogen atom, if you will. I'd like you to imagine the big blue arrows to be the external magnetic field into which we place the sample. So the individual green spins act like little bar magnets, and they align themselves to the external magnetic field. So that's our family of spins that we're going to manipulate. But now we can look on the right-hand side here. This arrow is the vector sum, the classical vector sum of all these little green arrows from the individual samples, sample elements on the left. So right now you can see it's very boring. All these arrows simply add up to one big fat arrow here. And on the bottom we have a graph of the net magnetization of the whole sample in the horizontal plane, okay? And you can maybe see the red line creeping across here. The horizontal projection of the spin is 0 right now. And so it's just creeping along here as time goes by, and it will stay this way forever unless we do something to manipulate the spin directions of the elements in the sample. So this will be our field of operation, shall we say, to examine what happens when we manipulate these spins in different ways. Right, so the first thing we have to investigate is something known as the oscillating radio frequency, or RF field, and we have to learn what the Larmor frequency is and how we can combine these things to find the phenomenon of magnetic resonance. Okay, so now we're going to do the next thing, which is consider what happens when you have all these spins lined up in this very strong external magnetic field. If we now imagine applying a sideways magnetic field in what we'll call the X or Y direction, then we can knock these protons, or these spins, whatever they are, but typically protons, off that initial vertical axis. And so I'm going to turn on an oscillating horizontal field, which will then explain. So here we're going to click this button. Boom. Look at what's happening. The spins are now oscillating all together in phase in a way that processes them around the external magnetic field. And as time goes by, the precession angle increases from 0 down to 180 and then back up to 0. This is the phenomenon of magnetic resonance, and it depends crucially on the frequency of this oscillating field, this magenta arrow going back and forth here. It has to match the frequency at which the spins want to do this. For a typical MRI machine, or here in this case an NMR demonstration, typical frequencies might be in the megahertz range, and it depends crucially on the strength of the strong external field. So depending on the strength of the external field, there is the so-called Larmor frequency at which the spins will precess in magnetic resonance as we see it here. We can play some games let me raise the frequency of the horizontal field going back and forth. I push this button once here, and let me reset the spins, and now watch what happens. So they're not exactly on resonance anymore. They precess around the external field, but the driving frequency is not the right one, and so they don't undergo the full magnetic resonance transition. What I can do is then, let's say, fix it and lower the frequency again a little bit by clicking the corresponding button over here, ready, and boom. And now in the demo, you see now we're back in resonance. And so we have tuned our RF radio frequency driving field to induce the spins to precess very nicely in the phenomenon of what's called magnetic resonance. So next comes the complication that the external magnetic field, the strong magnetic field, is never perfect. There are always variations, even if they're very small at the few Gauss level, that muddy the waters initially, and we'll have to cope with that. So let's see what we mean by internal field gradients and what that does to the behavior of the spins. So remember I said the blue arrows represent the very strong external magnetic field, but now in the demo we can vary that field strength. It won't be quite constant anymore across the volume of our sample. So there's a button here I can push that turns on field gradients, which don't instantly show up. But now watch what happens if we turn on the oscillating field at the Larmor frequency and watch the behavior of the spins. Ready, and boom. So the precession is starting on the spins, but look at on the left what is happening here. They're no longer in step. Why is that? Well, it's because each one is precessing at a slightly different frequency on account of the fact that the field gradients are present now. And so that makes the precession frequencies slightly different for each one of the spins. This down here is the projection into the XY plane, which is the horizontal plane in this demo, of the net spin or net orientation of this whole sample. And you can see here how it is no longer perfect. It's dying out. So to better illustrate the effect of these field gradients, let me pretend for a minute that they don't exist. And I want to apply an external RF magnetic magnetic field that lasts just long enough to rotate the spins by 90 degrees. In other words, moving them from the vertical direction here into the horizontal direction. In this simulation, that takes 2.5 cycles of the applied RF field. So I'm going to count it out and show you what happens in a perfect magnetic field before the gradients are turned on. So ready, I'm going to count it out. Here we go. Ready, and 1, 2.5. Voila. So what do we see? We see over here that the spins in the sample of a perfect magnet have been rotated by 90 degrees with respect to the vertical, and they now circulate here. You can see the vector sum of all their spins, and the readout, so to speak, in the xy plane of the degree of magnetization has jumped from 0 to 100%, and it will stay there forever in a perfect magnet. But now let's suppose we turn on the gradient, which in the real world is there all the time, but which we can now selectively turn on by clicking this button. Ready, and boom. Turn on the gradient, and notice how the spins are now getting out of step with each other, and the net magnetization, as computed as the vector sum of all the individual spins, quickly deteriorates to 0. So here it goes from 100%, and here it's crashing down to something close to 0. So that is really what we see in a real system, but without the luxury of being able to turn the field gradients on selectively. So in fact, what we've just seen is an example of what's called free induction decay. Let me show you that from start to finish without the artificial turning on of the gradient, so you can see how this simulation represents the phenomenon of free induction decay. So here we are at the beginning. What we'll now do is turn on the field gradients right from the get-go by clicking this button over here. And you'll notice that the projection in the xy plane is 0. That is because the sum of the spins is all vertical direction. So now let's apply what we just called a 90-degree pulse, 2.5 cycles in the simulation, and watch what happens. Ready, and 1, 2.5. Voila. So you see that the spins got rotated by 90 degrees, but they immediately started getting out of step with each other because they're in slightly different magnetic fields from place to place. And so in the xy plane, we see the magnetization go from 0, pop up to some large value, and then crash back down. And so that is the so-called free induction decay. It measures how long it takes here the spins to get out of step with each other in the material that we are inquiring about. Over here you can see how the net magnetization, first it spiraled down to the 90-degree plane, but then it quickly died out as all the spins got out of step with each other. In our simulation, we have about 100 spins, and so here you can see some partial realignment of the spins just because we're dealing with a sample of just 100 spins to play with, and not on the order of an Avogadro's number of spins. So this blip right here is the simulated version of what we call free induction decay. So next we're going to consider the first of the phenomena that are of importance when using NMR to do things like create MRI images. When the spins are flipped by 90 degrees, then imagine they are like little bar magnets, and so there's a interaction between the spins with neighboring spins, and this is called the spin-spin effect, and it leads to a phenomenon called T2 relaxation. And that's our next thing to try to simulate in order to understand what's going on. So we start again with our system in its initial configuration with the spins all pointing up in the external magnetic field. All the spins are aligned, and to understand this spin-spin effect, allow me to not turn on the field gradients. Imagine that the magnetic field is perfect, and so now when we flip the spins by 90 degrees, they will stay perfectly in step with each other initially, okay? So again, in this simulation, that corresponds to an external RF magnetic field pulse of 2.5 cycles. So here it comes, ready, and 1, 2.5. Voila. So the spins are now flipped 90 degrees, and they're all staying perfectly in step with each other, and the net magnetization stays large. And so here we see that the XY projection of the total spins stays at essentially 100%. But now imagine, please, that the spins, they talk to each other. They're like little bar magnets that are kind of close to each other. So as time goes by, they can interact by exerting a small magnetic torque on each other. So in the simulation, there's a button where I can turn on this spin-spin relaxation. And I just did that. Clicked this button, turned it on. Now watch what happens. As time goes by, the spins start perturbing each other. They don't all stay perfectly in step, and the net magnetization starts to get smaller and smaller, as you can see here. So this is the model for the so-called spin-spin interaction, where each pairwise the spins can perturb each other's motion slightly, and the thing dies away. That is to say, the net magnetization in the horizontal plane slowly dies away. So that's what's illustrated here. You notice it's not a perfectly smooth curve, and again, that's on account of the fact that we've only got 100 spins in our simulation, and so there's some granularity to the resulting picture. But this fall off here is the spin-spin interaction effect. So we can't actually measure this terribly easily, because in addition to this interaction, there's also the effect of the field gradients. But now we get into the most complicated bit of this demonstration to understand what's going on with the so-called spin echo effect, to actually measure this relaxation time, this exponential fall off of the spin-spin correlation, which is characteristic of the material that we're working with. So let's start again and see if we can get this spin echo effect to show up. What we're going to do is turn on the T2 relaxation effect. We're going to turn on the field gradients that are inescapably there, and we're going to start with a 90-degree pulse. Ready, and 1, 2.5 cycles. Notice how the spins quickly get out of step. This is our free induction decay effect right here, and the net magnetization has clearly fallen close to zero here, right? So now the famous trick is we're going to apply a 180-degree pulse, and what that does I will explain as soon as we do it. So in the simulation, that is 5 full cycles of the external RF field. Ready, and 1, 2, 3, 4, 5. And we applied it right here around 35 or so. So still the net magnetization is close to zero, and all the spins are still processing in the same direction. But now the ones that were furthest ahead are the ones that are furthest behind, because we've kind of flipped over the phase of the spins, all of them. And so now we're waiting for the spin echo to show up, where they're going to get back in step with each other, because the fastest were the slowest and the slowest were the fastest. Here it comes. Here comes the spin echo coming up. You see how the net magnetization is growing, and it dies down again. So the height of this peak compared to the height of this initial peak, this drop-off is the T2 effect. We didn't get to watch it continuously because of the dephasing of due to the magnetic field gradients, but we've allowed ourselves this trick to measure this spin echo coming after a certain length of time. So maybe you didn't find that entirely convincing. Let's make it a little easier by cheating a little bit. Let's say that we have the magnetic field gradients turned on, but we'll not turn on the T2 relaxation effect explicitly. We'll just see this spin echo effect as strongly as we can make it. So we'll start with a 90-degree pulse as follows: 1, 2.5 cycles. So there we are. Here's the free induction decay blip, and very quickly all the spins get out of step here on account of the field gradients. So they're all processing at slightly different rates, but now we're going to collectively flip their phases by 180 degrees with a 5-cycle oscillating field. So I'm going to count out 5 again. 1, 2, 3, 4, 5. Bing. Okay, so that was applied right about here. So between here and here, that's the time elapse for the initial dephasing of all the spins. And now we just wait, because as time goes by, the ones that were fastest are now, they were furthest ahead, now they're the furthest behind. And so as time goes by, they will eventually catch up with each other, and here it comes. Here comes the spin echo. See, it's rising. It's rising. The net magnetization increases. You can sort of see it here. And then, boom, we go over the top, and things get out of step again. So that's it. So between here and here, we let them get out of step, and we flip their phase. And then after an equal amount of time, they come back into step, and this is the famous spin echo. So the difference in height between here and here is, if the T2 effect were enabled, that height decrease would tell me, how much of the T2 physics was going on between here and here. The fact that these are not quite the same height here is just an indication of me not timing the pulses perfectly, and so they don't come back quite 100% into step, but only sort of close. Nevertheless, this is our illustration of the so-called spin echo effect. So T2 that we just looked at is an effect of the spins interacting with each other in the sample and slowly getting out of step. That's one bit of physics. But there's a second bit of physics that we can investigate. If we allow a spin all by itself to sit in the matrix of material that it's sitting in, eventually it can give some of its energy away to the so-called lattice, the environment that it sits in. So this phenomenon is called, or is measured by measuring something called the T1 relaxation time. And I want to show you that next with our simulation here. So here we are again at the beginning. What we're going to do this time, though, is let us pretend that we have a perfect magnet, so the gradients are turned off. And let us, right from the get-go, flip the spins in the sample by 180 degrees, which, again, in this simulation corresponds to pumping them with 5 full cycles of the external radio frequency field. So 5 cycles. Here we go. 1, 2, 3, 4, 5. Okay, so they're flipped over, so to speak, right? And in an imaginary world, we could let them sit here forever, right? But now the physics idea is that as time goes by, they give away this energy. They were in their low energy configuration pointing along the magnetic field. Now they're in their high energy configuration pointing opposite to the external magnetic field. So let me turn on the T1 relaxation effect here, and we'll see what happens. Boom, turn that on. So now, as time goes by, we watch this process here, and see, these guys have flipped over. Some of these are turning green on us. They're not in their high energy state anymore. They've flipped over into their low energy state. And so the net magnetization here, you can see the net magnetization vector. It's kind of shrinking, right? It's not turning, it's actually shrinking. And as time goes by even more, eventually you can see what's going to happen. It's going to end up pointing in the original direction again as more and more of the spins in our sample give away their excitation energy to their surroundings, jargon word, the lattice, and eventually everything will be lined up back where it was originally. That's the T1 effect. That's the effect of spins giving away their energy in some process that we don't specify, but it's just giving away their energy, and the net magnetization slowly grows back to the original value that it had before. You'll notice down here that we don't get to see anything. Just have this the blip as the spins pass through 90 degrees, and then it just stays very small thereafter. So there's actually no measurement to be made here yet, so we have to do something, and that's the next trick that we're going to learn. So the relevant trick here is that we're going to again apply some pulses. The first pulse that we apply will be the 180 degree pulse that turns the spins over with respect to the external field. But we want to actually measure to what extent the spins have gone back to their original direction. So the game is we're going to apply a 90 degree pulse at a time of our choosing, and that will put the magnetization into the XY plane, and that will give us a signal that we can measure. And by changing the time intervals of that second pulse, we can map out the exponential T1 response. So let's see that in action. We can simulate the T1 effect in an idealized way right now. Let's pretend that there are no gradients in the magnetic field, but there is this T1 effect here. And now imagine in this idealized situation that we flip the spins by 90 degrees into the plane where we can see the amount of magnetization that there is. 2.5 cycles. Ready? 1, 2.5. There. So here the spins are in the XY plane, but you can see how the net magnetization, it's staying coherent. There are no gradients in the field, but as time goes by, the net magnetization goes more and more into the original vertical direction. And so the projection into the XY plane is dropping off exponentially here. Why is it exponential? It's actually easy to see. Just the number of spins that flip is proportional to how many spins you have left that are not flipped. And so that automatically leads to an exponential style distribution. So as time goes by, this exponential maps out the T1 response that characterizes the particular material that we're using. But of course, this isn't the way we can really do it, because in the real world there are gradients, and so we need one more trick. So here we are at the beginning again, and we'll look at how to measure T1 more realistically. So we turn on the field gradients, so the magnet is not perfect. Then we turn on the T1 relaxation effect. And then the next step is we will flip the spins by 180 degrees and then wait. So ready, and 1, 2, 3, 4, 5. Okay, so not too ideal, but we see that the net magnetization here, as time goes by, it's getting smaller and smaller. So this was the magnetization going through 90 degrees, and then here this is the bounce a little bit, and then here we are with a very low level of detectable magnetization in the XY plane. But as time goes by, the net magnetization shrinks, goes through 0, and then starts growing again. So to see at this moment in time what the magnetization is, we can do a 90 degree pulse. So let's do a 90 degree pulse, 2.5 cycles. Ready, and 1, 2.5. Boom, here's the signal. You see? So this shows us the degree of magnetization that the sample has at this moment of time, delayed by some measured delay after the original 180-degree pulse. So by mapping out this peak as a function of the delay time, we can measure the T1 relaxation of the sample independent of the complication of the magnetic field gradients. And we get at the underlying physics of the T1 process. So that's about it. I've tried to show you how the T1 and the T2 mechanisms work in nuclear magnetic resonance with our simulation. But there are lots of things that we haven't mentioned, and it takes a while to master the physics of what's happening here. So you might ask your instructors or do some reading about the next level of details here. For example, the question is, how are classical spins, like in our demo, related to quantum mechanical spins that allegedly describe the behavior of protons in organic materials, for example? And the short answer is that time dependence of the expectation value of quantum spins is the same as the time dependence of what happens to classical spins in a magnetic field. So the demonstration that we've done is actually accurate in how it depicts that part of the physics. We haven't talked about what is the actual mechanism of the T1 spin lattice relaxation phenomenon. In other words, the spins have to give away their higher energy to, as we say, flip back to the lower energy. And how does that interaction work? We haven't touched on that. Of course, the next thing is, you want to know, how does a magnetic resonance imaging machine selectively measure T1 and T2, not just for a little sample like what we've simulated, but for every spot in, say, the body that is being simulated? And the answer is gradient fields. So you adjust the Larmor frequency of the little sample that you're interested in by applying a suitable field at the spot that you're trying to measure it. So that's the sort of the engineering aspects of this that we haven't talked about at all. And then the next step from there is then how do you use the T1 and T2 relaxation information to make actual images for MRI type scans. So we haven't touched upon that, but you can read up on it. To conclude, we've taken a look at magnetic resonance imaging in a VPython demonstration, and I'll close by saying once again that you can try this out for yourself more slowly, and you can see how it works in detail. And so the program is free to use, and it's available here at this address on this slide, and there's also a QR code that should take you there. So thanks for your attention, and happy simulating. Bye-bye.